Thank you, Dr. Garg. Hello, everyone. This is Krishna Adhikari. I am a PhD student at the University of Kansas. Today, I am here to present my research on development length and splice strength of high-strength reinforcing bars in high-strength concrete. Under the supervision of Dr. Darwin, my advising committee includes Dr. Matt and Dr. La Paz. To begin with, this is the outline of my presentation. We have a subchapter in ACI building code for development length, and these provisions were introduced back in 1995 based on limited test data. The test data at that time includes compressive strength up to 8 KSI and bar stresses below 115 KSI, mostly under 80 KSI. Since then, there are only two major updates in SCI code regarding development length equation and provisions. One in 2008, based on our past study in KU, to simplify and improve the accuracy of development length equation. And another in 2019 with the aim to partially patch the unconservative nature of the provisions for high strength rebar. That provisions requires the transverse reinforcement in lap splice region. So this is the current design equation for development length. Here Fi represents yield strength of the bar, F'(C) compressive strength of concrete, and there are other factors psi of T, psi of E, psi of S, and psi of G to account for casting position of bar, surface condition, size of bar, and grade factor. Current SCI provisions limit F'(C) to 10 KSI while calculating development length. Though our past research has shown that, as you can see, there is F'(C), root under F'(C), square root of F'(C) to account for the contribution of concrete strength to the development length. Our past research has shown that instead of square root of F'(C), if we use quarter to the power of F'(C), then it will represent weight. However, because of long-standing use of square root of F'(C), and it is safer for the concrete strength up to 10 KSI, ACI 300 is still using square root of F'(C) with the limitation. And also, as I am researching on high strength rebar, the current ACI provisions has grade strength factor for high strength bar, ranging from 40 to 100 KSI. So, ACI subcommittee 48 is maintaining the database, which is the backbone for the current provisions. We can see in two charts. The first chart is for specimens without stirrups in splice region, and the second chart is for specimens with stirrups in splice region. Vertical axis represents developed bar stress, while horizontal axis represents concrete compressive strength. We can see all the tests were conducted mostly for bar stress under 80 KSI, but there are adequate data to validate the current provisions for bar stress above 80 KSI also, but with concrete compressive strength below 10 KSI. Nowadays, high strength steel and high strength concrete are common, and ACI could also use of high strength steel, 100 grade steel. But if you see the top right quadrant in both charts, we don't have any yet, right? So to use efficiently the high strength material, we want to see. We are basically targeting to develop basic data for high strength rebar cast in high strength concrete, and to formulate design criteria for reinforced concrete structure. These are objective of my research. For that, we have designed test matrix including 39 splice specimens with different variables that are known to affect bond strength. As we are targeting high strength concrete, our concrete strength ranges from 12 KSI to 16 KSI, and we are targeting bar stress from 90 KSI to 140 KSI. Also, as bar size has, like I told you before, we have a bar size factor. That means in current ACI code, that means bar size also has effect on body strength. So we are using different bar sizes and different concrete cover And confining reinforcement, KTR is the transfer reinforcement index as defined in SCI 48R. So our that term ranges from 0 to 3.1, and to get the target bar stress, our splice length ranges from 33 dB to 54 dB. dB represents the bar diameter. So this is the schematic representation of our experimental setup. We have a strong floor in our lab. We are using 4-point welding test. Our lab splice region is in constant moment region. Now we have two simple supports in the middle, and we are applying load at the two extremities. We are using hydraulic jack to apply the load, and spreader to distribute the load on top of the beam, and we have load cells to get the load data. Also we have potentiometers to measure the deflection at two extreme ends and on at the middle. And this is the real setup in the lab. We can see here, as I explained before, this is the beam. Please pardon me for the quality of the picture. Beam is resting on two concrete blocks, as one concrete block has roller support and another on pin support. And we have very important thing, computer here, get all the data. And you can also see some cases and conduits under the black plastic under over here. So let's discuss about the results. These two charts are similar to that I explained before, but the red dots represents new data from our research. We have several data for the specimens we disturbed in Splice region, but we will be adding more data because this is the research in progress, so we'll have more data for the specimens of students also. Today we have tested 27 Splice specimens. And we are comparing basically to SCI 48 equations and provisions, and also with SCI 31819 building code provisions. We are comparing our measured bar stress with the calculated bar stress. In this chart, in vertical axis we can see measured bar stress, and in horizontal axis calculated bar stress based on descriptive equation of SCI 48. We can see here that most of the data are below the red line, equivalence line. That means SCI 48 descriptive equation is overestimating the body strength of the bar stress. Here, blue dot represents number 8, bar says specimens. W means with a transfer reinforcement in splice region, and W/O means without transfer reinforcement in splice region. So red dots is for number 11, black triangle for number 14, and blue circle without shade is for number 8 without disrupting splice region. And we got mean test over calculated ratio of 0.93 with coefficient of variation 0.07. And this is the similar comparison, but this is with the design provision of SCI 48. Here we are using strength reduction factor 5 0.82 as recommended in SCI 48. And the mean is 1.15 and coefficient variation is same 0.07. And we can see almost all data on the upper side of the red line, means this is quite safe to calculate the development. And now we are comparing our bar stress with SCI 31819 design equation and provisions, bar stress calculation 31819 equations. We can see the data here are mostly over the red line. That means SCI 31819 is also generally safe, but we have 3 specimens under that red line, equivalence line. But if you see the coefficient of variation 0.3, the data looks quite scattered, and mean is 1.18. So to that, our conclusion is that SCI 48 our descriptive equation overestimate the bar stress or in another term body strength for high strength rebar casting, high strength concrete. But SCI 48 are 0-3 design equation and design provisions. It looks safer to calculate development length and splice length if we are using high-strength rebar in high-strength concrete. SI 219 provisions looks generally safe, but exhibits greater standard. And it is not always conservative, even with limit of apparentcy. As I said, we have limit of square root of apparentcy to 100 psi means 10 psi. Even if we use 16 psi means we cannot efficiently use that concrete strength. So our future work includes fabricating and testing of other specimens, more specimens, and we will do comprehensive data analysis, and the ultimate goal is to formulate design criteria. I would like to acknowledge our research sponsors: CRSI Education and Research Foundation, Commercial Metals Company, Nuclear Corporation, Steel Dynamics, Cascade Steel Rolling Mills, and the University of Kansas Endowment Association. At last but not the least, I would like to thank SEI for giving this platform to present my research, my professors, my family members, and all my grad and undergraduate friends. Now I open the floor to the questions.